Hello everyone. Today we are going to learn about phases of compiler in detail. So I've already explained in the previous video about the language processing system. We have a source program which we write in C, C++ language, Java language, and then preprocessor is used to remove the shortcuts which are defined using hash define, hash include, and the actual code is put up in the program, and we get the modified source program which is given as an input to compiler. Compiler will convert it into target assembly level program which machine understands. Then target assembly level program will be given as an input to assembler. Assembler will convert it into relocatable machine code. Okay, that is 0 and 1s in the file, and the file is relocatable. You can put it in any memory and anywhere in the memory. So that relocatable machine code is given as an input to the linker. Linker will combine all the relocatable files which are at different places in the memory into one single file, and your program will be in the new state. So new program as whole will be created. Okay, and that new file which is created by combining all the relocatable files will be given as an input to loader, and loader will load that file from hard disk or solid state drive into your main memory, that is RAM, and target machine code will be generated. So this is the flow for language processing system. Now as you all know, in language processing system, second step is compiler. Okay, inside compiler only we have to perform 6 phases. There are 6 phases are there inside the compiler. So high level language, that is modified high level language, is given as an input to the compiler, and compiler will apply these 6 phases and will give us the output, that is object code or machine executable code which machine understands in the 0 1 format. Okay, which machine will understand. So source program, lexical analyzer will be applied, then syntax analyzer will apply to your source program, semantic analyzer, intermediate code generation, code optimization, code generation, and the target program will be given as an input to assembler. So first step is lexical analysis in compiler. So it is also called a scanner. It takes output of preprocessor which perform file inclusion and macro expansion as input, which is in pure high level language. It reads character from source program and groups them into lexim. Now what are lexims? Sequence of characters that go together. From the lexims, tokens are made. Lexical analyzer input is source code, okay, which is created after pre-processing step, that is after removing all the shortcuts. Actual code is put up in the source code by the preprocessor. So that source code will be given as an input to lexical analyzer. And lexical analyzer will convert the source code into tokens or words. Now each lexeme corresponds to a token. So tokens are defined by regular expression and used by finite automata which are understood by lexical analyzer. You can draw the finite automata which is understood by lexical analyzer. So it removes all lexical errors like comments, white spaces. Those are the lexical errors. In C program, suppose you have opened the comment and then you forget to close the comment at the end, then you will get the lexical error. Even for the white spaces, you get the lexical error. And it uses symbol table for giving token number. Every token is given the number inside the symbol table. Symbol table is a data structure for storing all the data like variable data or the data type details. So now this is a line which is written in the C program. How the tokens are made? Every keyword, identifier, operator, constant are considered as individual token. Now here int is a keyword which is used in C. There are 32 reserved keywords in C. Int is one keyword. So this is considered as a one token. Then X is an identifier, nothing but a variable names which we can give any name. So this is also considered as one of the token. Then equal to is an operator like plus, minus, into. So it is also considered as a one token. 10 is a constant. It is also considered as a token, and semicolon is the end of statement. So 1, 2, 3, 4, 5. There are 5 tokens in this one line. So lexical analysis will take the program and like this it will make the token. So in this there are 5 tokens. Then next phase is syntax analysis. Now it is sometimes called as parser because it constructs the parse tree like this. Syntax analysis phase always construct the parse tree like this. Tree it is. Okay, tree has a root and branches and the nodes. So in the circle which you can see are the nodes, and the arrows are considered as what? Branches. And it is like a tree. It looks like a tree. So it takes all tokens one by one from lexical analysis phase and uses context-free grammar and push-down automata to construct parse tree. In lexical analysis, we were using what? Finite automata and regular expression. Here we are using context-free grammar and push-down automata to construct parse tree. So parse tree is also called as derivation tree because we derive the tree based on the tokens. So parse trees are constructed to check for ambiguity in given grammar. So these are the tokens which are the output of the lexical analysis phase. Based on these tokens, I have to draw the parse tree. That is the output of the syntax analysis phase. The syntax analyzer will draw the parse tree using push-down automata and context-free grammar. So we have a syntax error when we run our program. We sometimes get syntax error or suggestions are given by the error handler. So what are this syntax error? It checks the syntax of the program and stores the extra data in the symbol table. So example of syntax error is, this is a program. Here three variables are declared a, b and z of type int, and z is equal to a plus plus b is written. Now there is a syntax error in the program because a plus plus is one token. Okay, this is separate and this b is separate. Plus plus is attached to a. Okay, it is for one variable and this b is considered another variable. So when you do a plus plus, you will get new value for a. Okay, and then b is there. So z equal to, it will be ab. There is no operator in between. So this is called a syntax error. So how it will calculate? There is no operator only. Into is not there, plus is not there. No operator is there in between them. So you will get syntax error saying syntax is wrong. So this type of errors are called as syntax errors. Then we have semantic analysis. Now input to semantic analysis is the parse tree generated by syntax analyzer. Now this is a parse tree generated by syntax analyzer as the output, which is given as an input to semantic analysis, which is the next phase after syntax analyzer. So it verifies the parse tree whether it is meaningful, correct or not. And it produces the verified parse tree. Output of semantic analysis is also a parse tree, but it is a correct and verified and meaningful parse tree, unlike syntax analysis parse tree. So it does the type checking whether type is correct, which is given to the variable, label is correct, flow control it checks. Also type conversion is checked from int to float, float to int. And also variable is declared or not is also checked. If you have not declared the variable, you will get semantic error. So gives semantic error suggestion to error handler, finds logical errors rather than syntax error. Syntax means way of writing is wrong. Semantic means logical error or meaning is wrong. So it checks the semantics or meaning of the program, store extra data in symbol table. Now this is an example of semantic error. Program is written, one variable is declared of type int, that is x, and another variable y is declared of type y. And it is written x equal to y. Now here there is a semantic error because both are of different type. You cannot write x equal to y. You cannot assign value of y into x. Why? Because x is of type int and y is of type float. So here you will get semantic error or logical error. Now next phase is intermediate code generation. It generates the intermediate code which is of form that can be readily executed by machine. Why we need to generate intermediate code? So that your code will be executed easily in the machine. Example, you can make intermediate code representation using postfix notation, syntax tree, directed acyclic graph also called as DAC, three address code, quadruples, triples. These are the ways to make intermediate code representation. You can write your intermediate code using these notations or using these forms. So intermediate code is converted to machine language using last two phases which are platform dependent. Till intermediate code it is same for every compiler, but after that it depends on platform. So to build a new compiler, we don't need to build it from scratch. We can take the intermediate code from existing compiler and build only last two phases. Example, every compiler will have this part same. These four phases will be same. So whenever you want to develop a new compiler software, you don't have to build it from scratch. You can take the code of all these four phases as it is because these four phases are common for all the compilers. Only the last two phases will be different. Okay, this is platform dependent phases, which varies from computer to computer or operating system to operating system. So these two phases will be platform dependent. You have to do it for your compilers. But this above four phases, you don't have to work on it. It is already available and it is same for all the compilers. So you can directly use. Now here one compound statement is given, that is all the operators are used in one only statement, x equal to a plus b into c. Now how I can represent this compound statement using intermediate code representation? We can put only one operator in one line. So t1 equal to b into c. I have put b into c part in t1 variable. Then in t2 variable I am putting a plus t1. And then whatever I am getting answer for t2, I am storing it in the variable or identifier x. So instructions mean one operation only. Only one operation used at a time in the each statement. So this phase generates an explicit intermediate representation of source program. Intermediate represent should have two properties. It should be easy to produce, easy to translate into target program. Next is code optimizer. This phase is optional phase, not compulsory, and it attempts to improve the performance of intermediate code so that machine code runs faster and takes less space. So code is transformed into code optimizer phase so that it consumes fewer resources. So there are two types of code optimizer, machine dependent and machine independent. Now three address code intermediate representation is given. T1 equal to B into C, T2 equal to A plus T1 and T2 is stored in variable or identifier X. Now after applying code optimizer step, what will become? T1 equal to B into C and X equal to A plus T1. You can directly put a plus t1 in another identifier. You don't have to go to temporary variable again. So this is a shortcut. It will take less space, less time and less resources to execute. Last step is target code generator. Now it is a final phase which generates the target code. It consists of relocatable machine code or assembly code. Memory location selected for each of the variable used by program. The intermediate instructions are translated into a sequence of machine instructions that perform tasks. What is the output of target code generation? Variables are assigned to register. Okay, like this. So move id 3 comma r2. So id 3 is moved to r2. Then multiply 60 to r2. Move id 2 to r1. Add r2 to r1 and move r1 to id1. So all over here assembly level mnemonic codes are used to, or assembly level programming is used to generate the target code or for doing the target code representation. So variables are assigned to register. Code is written in such a way that machine can understand and also register allocation, instruction, selection, etc. So output dependent on type of assembler you are using. So this was all about phases of compiler. Thank you.